Rainy Monday morning. For those of you who don't know me already, I'm Paul Evans. I'm the co-leader along with J.R. Schmidt of IRG2 of the MRSEC. Today, Paul Voiles, the MRSEC director, and I will give the last of the lectures about scientific concepts that underpin our center as a whole. And because Paul and I are going to team up to do this, we'll split the time. I'll go through the beginning. Paul will tackle some topics in the middle, and I'll come back at the end. And this is really something that we've generated together. The topic today that we're going to cover is the structural principles that underpin the understanding of amorphous materials. These are materials that cut across both IRGs, and in fact, some of the seeds in the MRSEC as well. And we'll talk about the means of their characterization, not just in an experimental sense, but in a descriptive sense, meaning how do you understand and discuss the complex structures of amorphous materials. So that's our goal for this lecture and for this time. And so we'll use our time like this. We'll talk about some very basic structural features. And these include the idea that there's not any measurable long-range order in amorphous materials, but that there's significant short to nanoscale order, meaning at the scale of bonds to nanometers, that there are ways of characterizing and describing the structure. And in general, we'll focus on descriptions that have to do with understanding the local configuration and in understanding that short-range order contribution, and these are all radial or pair distribution function based ideas that we'll talk about. Then we'll apply these ideas in 4 sets of systems: in metallic glasses, molecular glasses, in so-called network-forming glasses, and finally in more complex oxide amorphous solids, and we'll give a brief summary at the end. As we go through, there are going to be many examples and citations to the literature. You'll find that there are articles and books and other reference materials that we refer to. They're all available here at this shortened link that I believe Carrie will be able to share with you as well afterwards if you like. So there are PDFs, hundreds of megabytes of PDFs there for you to look up the details. So let's get started. I will first start by going through what we should think about an amorphous material being first. So an amorphous material is atomic solid or solid-ish material that has well-established short-range order, meaning that the bonding configuration or the other local configurational issues are well satisfied, that there are well-established nearest neighbor distances, that the bond angles are approximately right, that atoms find appropriate coordination numbers, and that these are structural features that are similar to the crystalline versions of the material. So if you have, for example, a metal that prefers a certain number of nearest neighbors, you may find a very similar number of nearest neighbors, at least on average, in the amorphous form. You can form, if you take care of bonding issues, you may form networks that locally satisfy bond angle issues, or in metals you may have to create local structures that satisfy not only the bonding, the nearest neighbor numbers, but local electronegativity considerations as well. These are materials that, because they're highly disordered on a global scale, don't exhibit Bragg peaks. So if you do a diffraction experiment, in this case an electron diffraction experiment at the lower right, you'll find that there are no Bragg reflections. I'm sorry, the lower right is the amorphous material here. There are no Bragg reflections, but you'll see a modulation of the intensity as you move towards higher reciprocal or what would be a reciprocal lattice, but a reciprocal space wave vector. And you'll find that there's a modulation in the intensity that has to do with the local order. Understanding and describing the structure of these materials is challenging because we have to extract information from this type of experiment. We'll talk about that In contrast, of course, a crystalline material, because it has long-range orientational and positional order, has this, this set of very well-established electron or X-ray reflections that are sharp and bright and isolated. You can learn about the structure by analyzing their intensity if you want to study single crystals. If you're looking for these kinds of ideas at any scale, you can do this. And so this is Paul's slide that compares two cities. It might be hard to see from the back. You can't read it, but maybe someone can name the city on the upper right. What city looks like this? This is a city that has local 3- to 4-fold coordination in the corners of the blocks. City like that. Pong, you just visited a city like that. Boston would do this. This is London. This one is Chicago or New York. This is New York, I think. And so you'll see that this scale idea extends all the way from the atomic scale to the scale of organization of other networks. So these are really network geometry issues at some level, and we'll think about those as well. Okay, so the goals, if you establish that there's this set of atoms in an amorphous solid, it's really not meaningful to know where all the atoms are individually. What is really important is to develop some structural description that allows you to interpret the ordering of the atoms and to learn about the properties of the resulting material. And so the goals of characterizing the structure of amorphous materials are to learn about the quantities that we can use to describe the structure. So these include the state of the atoms, the chemical state, for example, the valence, the coordination numbers, their packing locally, and it's become clear over about 100 years of working with amorphous materials that you can systematically understand this order, modify it, and have a tremendous impact on the stability, the crystallization behavior, the electric permittivity, elastic properties, and so on. To understand these phenomena, or these ideas, there are many, many structural tools that are available. We will highlight the scattering tools. So these are really the first three on this list: X-ray scattering, neutron scattering and diffraction, electron microscopy and scattering. There are many, many other tools as well, including Raman, NMR, some inelastic techniques. We won't focus on those as much. We'll talk a little bit about X-ray spectroscopy today as an example. But really what we want to do is show that the quantities that tell us about the things in the top line can be extracted from scattering measurements and from informed also by some of these other techniques. So let's talk about the scattering measurements for a second. There's one point I want you to take away from the scattering, and that is that you can do a complicated looking experiment, but you can extract a very fundamental and relatively straightforwardly described quantity that you can use to interpret the structure of the amorphous solid exactly, or at least precisely. So what we want to do, if you're doing a scattering experiment, you can imagine that this is an electron microscope or a neutron reactor or a neutron spallation source or a synchrotron or an X-ray tube source. All sorts of things could be down here in this continuous source. Then there's a sample here that this beam of particles strikes, and then you quantitatively measure the number of particles that make it to this detector that are scattered through this angle 2 theta. And then you sweep that angle and you map out that intensity as a function of the angle. And you can describe the geometry of this problem more fundamentally than using just the angle by using this wave vector Q. The wave vector is the difference between the incident and final wave vectors of the particles. That Q is of fundamental interest. That's really, really precisely defined, as I'll show you. And we can take the intensity that we measure and transform it into a structural description. So The fundamental structural description that we want is something called S of Q. That is a parameter that describes the ordering. And it turns out that the S of Q is exactly the intensity as a function of Q divided by how many atoms you have and how much each one scatters. That works, exactly. And even better, S of Q turns out to be the sign transform of the atomic density. So if you have the atomic density, you can predict S of Q, or there's a problem here because this has a phase factor we don't know. We can't quite go backwards, but you can almost go backwards. If the data is, if the data is really good, you can work backwards from S of Q, and you can learn about something called G of R. And G of R is what's called the radial distribution function, sometimes called the paired distribution function. It tells you about the arrangement of the atoms. It tells you the distances and numbers of pairs of atoms. And if you have very good data, you can go from S of Q, which you measure here, there's S of Q buried into this expression, to G of R. And how you do this is the part of the science of X-ray or neutron or electron scattering, but you can get good measurements of this. And we'll see this throughout the talk today, that there are excellent measurements of G of R. So if you have, I should tell you about one more interesting aspect of this. This is really more background on how that particular idea works. But if you look carefully here, this is how you go from the fundamental description of the intensity to the extraction of the relationship between the intensity and the atomic number density. But if you look carefully here, you'll see that there's a component that's local, this first term of this sum, and a component that tells you about the shape of the particles. We're going to ignore the shape of the particles, and we'll just look at the local contribution. But this, just remind you, this is exact, and it depends on how much each component scatters. If you want to have a solid that's composed of more than one ion, you might want to know how the pairs of ions are correlated with each other. For example, if you have an amorphous silicon-germanium alloy, you might care about whether silicon has silicon neighbors or silicon has germanium neighbors. In general, that's very hard to get because I of Q is just one scalar. But I'll show you in a second how we can manipulate these F's to get some more information about that. Okay, so let's now start abstracting towards the structure and think about how we can use this G of R that we can measure to describe the structural aspects of these amorphous solids. So if you start with any non-crystalline material, we can construct this radial distribution function or pair distribution function G of R, and I'll just caution you that people go back and forth. And you can see that it immediately will depend on the local structure of the material. So here are two candidate materials. There's a crystalline solid on the left and an amorphous solid or a liquid, a frozen, instantaneously frozen liquid on the right. And you can see that if we integrate the number of atoms that appear at a distance r within a stripe dr wide, you'll see that at the first nearest neighbor's distance, these solids are very similar. They have similar numbers of nearest neighbors at a similar distance. That's because the local packing is satisfied. If we go to larger distances, we'll find that the degree of modulation, that is, as you go further away, these distances become, these pairs become less well defined, and the modulation in G of R disappears in the amorphous solid, but is maintained out to arbitrary distances in the crystalline solid. So that's a simple interpretation of G of R. You can immediately measure the number of nearest neighbors. So if you can do this, this is easily determined. This is an example drawn from a very nice textbook on X-ray scattering here. This is and extract, this is the non-periodic arrangement we want to think about. This is on the right, S of Q and G of R extracted from that S of Q for a liquid nickel. And if you integrate this gray area here, integrate this gray area, as a, you'll find that you can count the number of nearest neighbors for nickel in liquid nickel. And it agrees with this very simple this very simple atomic packing type of argument. And then there's more information further out, and that's the subject of the rest of the lecture. Final thing I want to say is I mentioned before that we might want to know about pairs. And the pairs may not be the same atoms. In fact, if we have two ions, alpha and beta, we could ask, what are the chances if I start on alpha that I end up on alpha, or I could end up on beta? Are you with me? And so that G of R now has to do with the likelihood of finding any atom, or the likelihood of finding an atom with the identity that we're interested in. And so we can define a new quantity, G alpha beta, that tells me about how many particles I find at distance r, or how many atoms, I'm sorry, I find at distance r of identity beta if I start on alpha. Are you with me? Then I can define from that, using the same math that I just showed you, you can define an S that's not the total S of Q anymore, but it's now the S for that pair, S alpha beta. Okay? Or if I could somehow measure S alpha beta, I could extract G alpha beta. So the problem is, how do I measure that quantity independently of the total S of Q? And the problem is there's not quite enough information unless you play some tricks. One of the tricks in X-ray scattering is that the Fs, this degree to which each atom scatters, it shows up here in this intensity, is an F for alpha and an F for beta. This is the total intensity. If I could vary Fs systematically, I can figure out which alpha, which one is contributing how much. And that's done using anomalous X-ray scattering. It turns out to be a relatively straightforward trick. It was first applied to these types of materials in the early 80s. And you can do that, and you can extract the S alpha beta parameters, and you can learn about the coordination of individual ions within the amorphous solid. And there are some examples. The earliest examples are with simple amorphous semiconductors, the germanium, okay, Carrie warned me that oh no, here it goes. The germanium selenide and germanium selenide 2, those were first studied in the 80s, and it works in a wide variety of materials. So finally, you can go back and you can extract these S alpha betas directly from your measurements of the intensities if you can figure out how to use the Fs correctly. And that really works. So I'll show you some examples of that later on. I think Paul will as well. So that brings us to the end of this introduction. We'll now go through several of these different examples of materials.
Which involves
switching
all the microphones. All right. Hopefully all of the various entities that should be listening in can now hear me as well. So I'll talk about a couple of different classes of amorphous materials, categorized primarily by their bonding type, which influences their short-range order. We'll start with amorphous metals and metallic glasses. These are metal alloys which can be made glassy by rapid quenching at sort of 1 Kelvin per second up to 10 to the 6 Kelvin per second. And they typically have applications that are driven by properties like their high Young's modulus at low weight, good corrosion resistance, biocompatibility, and particularly their high processability. That I really like. Here are some examples that I've stolen off of Jan Schorer's website at Yale of the ability to process metallic glasses into a huge variety of structures at a bunch of different length scales by raising them into the supercooled liquid state, where they're highly viscous liquids, and deforming them in that state to fill a mold. And the mold can be macroscopic all the way down to nanoscopic. These are 25 nanometer diameter nanowires covering large areas. Then cooling the liquid back down to form a solid with no, essentially zero change in shape. So the first model for the structure of metallic glasses was inherited from ideas around the structure of metallic liquids that were developed in the 50s and 60s. And the model is dense random packing of spheres. So this is the sort of simplest possible model for the structure of metal atoms, and that is that they are all hard spheres that are attractive up until they touch and then repulsive. And you want to pack those together in a way that maximizes the filling of space, but without introducing any crystallographic order. So this is one of my favorite figures from the early literature. This is a model of a dense random packed solid by Bernal, published in 1964, which was created by taking a bunch of ball bearings, putting them in a rubber bag, shaking the bag really hard, and then filling it with epoxy, letting it cure, and peeling the bag off. And you can see that the surface has some, so you can see that there's some ordered regions that are from the order imposed by the surface of the bag. And then the poor students working on this project took this mass of ball bearings and sectioned it on a bandsaw so that they could measure the center position of every one of the ball bearings to turn this into a three-dimensional model. Now we would do this on the computer and it would be a lot less messy, but it worked. And particularly they could compare the experimental results, or the calculated results, to experimental results on the structure of liquid argon measured using X-ray scattering to determine the pair distribution function. And the agreement's not too bad. Okay, so, but, oh, now I can't advance the slide. So.
You want to try tapping on it from within the laptop?
Okay. I'm not, unfortunately, I don't see the same thing. Yes, no.
I see a little X at the top of the editing bar on the left.
Oh, now what have I done? Screen sharing. Sorry.
While we work on this, are there any questions so far? I think Carrie will probably figure this out, and Paul maybe can answer some questions while Carrie gets this rebooted.
And then just share, there are two choices of what to share.
The two sort of compositions, you only need like two compositions there to do that sort of variability and identify the output.
Okay.
Oh, yeah.
I think we're back.
The anomalous. Yes. Looks like Paul's ready to start.
Okay.
Sorry, we didn't have enough time. Just keep that question in mind.
No, keep going. It's here. The question is whether it's going out electronically or not.
The question was, in practice, how many X-ray energies do you need to be able to make that type of anomalous scattering experiment work? In general, if you have a good model, then 2. 3, or you can do it continuously and fit with more parameters. It becomes a little bit uncertain how you have to have a model for how those F's get summed up. But we'll come back because this is at the heart of it. This comparison
That looks promising.
And scattering data.
All right. Now, oh yeah, it says I'm sharing my screen. All right. I promise not to press the wrong button again.
It says forward and back.
No.
No, forward and back.
Ta-da! Okay, so once you have one of these kinds of models where you know the positions of all the atoms, you also want to be able to develop some kind of abstract description of what those atomic positions are. There are a lot of different ways to do this, but the one that I'll highlight today is the construction of a Voronoi polyhedron around each atom. So in 2 dimensions, the idea is you want to find the area of space that is closest to its central atom compared to all the other atoms. Geometrically, you can do this by drawing the line connecting each atom to its neighbors and then constructing the polyhedron made out of all the perpendicular bisectors. This is in 2D. In 3D, all of the bisecting lines become bisecting planes, and you get a polyhedron surrounding the atom instead of a plane shape. And there are characteristic polyhedra for all of the simple crystal structures. So here's the one for a BCC crystal, here's FCC crystal. HCP is the one that's, to my eyes, easiest to see the relationship between the coordination tetrahedron, or the polyhedron, and the crystal structure. So if you may use this kind of analysis on a dense random pack structure, you'll find a significant number of icosahedral arrangements of atoms. For an icosahedron, the Voronoi polyhedron is a dodecahedron. It's a polyhedra with only pentagonal faces. So it's nothing but pentagons. That means that it has only 5-fold rotational symmetry, which is not allowed for crystals. You cannot tile all of 3-dimensional space with objects that have 5-fold rotational symmetry. This was pointed out by Frank in some of the earliest work on undercooling of simple metals. That an icosahedron is a close packed structure at the nearest neighbor level. It has the same number of nearest neighbors as FCC or HCP, but it can't tile space. So if you form icosahedra in the liquid, it will tend to stabilize the liquid against crystallization, and it'll do the same thing if you can cool the liquid quickly enough to form a glass. So dense random packing gives us a good place to start, but we can build on this idea of efficient packing of space to accommodate more than one atom that have different size. This gives us, in the first instance, the zoo of polyhedra identified by Frank and Casper, and then added to at different higher coordination numbers later on to make this set of Z clusters, which are discussed and summarized in this paper by Cheng and Ma, from which I stole this nice diagram. These are polytetrahedral structures, so they're made by close packing sets of tetrahedra to make larger polyhedra. It's also possible to work out the mathematics of what are the preferred coordination numbers as a function of the radius ratio of 2 different atoms. And that's been developed initially by Takeshi Yagami and then more extensively by Dan Miracle and his co-workers. So you can see if you have a little tiny atom and you're packing large atoms around it, only a few large atoms will fit, and that should give you a preferred coordination number that's relatively small, in this case 4. But as the central atom gets larger, you can pack more and more atoms around the central atom, and the coordination number will increase. But the diagrams are the sort of preferred coordination numbers. Coordination diagrams, where the outer atoms are just touching. But you can have intermediate states where the atoms are either too crowded or too far apart. So this is a 5 where the atoms have spread apart just a little bit, and therefore the packing efficiency is not as high for this ratio of atoms as it would be for either of the ratios on either side. Now, real metallic glasses exhibit what's called chemical short-range order. A dense random packing of multiple atomic species has every atom next to every other atom determined randomly only by the concentration. But we know that real metal atoms have preferred nearest neighbors determined at the macroscopic level by the heat of mixing between the two species. And we know that that happens in metallic glasses from the same kind of partial pair distribution function data that Paul was talking about earlier. So here are two examples. On the right-hand side, this is an anomalous X-ray scattering experiment on lanthanum, aluminum, nickel using anomalous X-rays at the nickel K edge. So the top trace here is the total radial distribution function. And then the bottom trace gives us the radial distribution function where we have now selected to have a nickel atom at the center of every one of our pairs of atoms. And that shows a large enhancement in this first peak and a reduction in the second peak. And by looking at the size of these different elements, the authors here conclude that this large peak means that there is strong ordering of lanthanum around nickel. So there's an excess of lanthanum in the first coordination shell of the nickel atoms compared to what you would expect just from the composition and a dense random packed arrangement. An equivalent experiment, or a similar experiment using neutron scattering is shown over here, whereby changing the isotope of nickel in an aluminum nickel neodymium glass from nickel 60 to nickel 58, it's possible to change the neutron scattering length of the nickel by a factor of 5 without changing its chemistry at all. By only changing the isotope. The reason that people don't do more of this is isotopically pure metals are fantastically expensive. So this represents probably $10,000 or $20,000 of just raw materials to make the samples. However, in the sample with the stronger nickel scattering, they see a distinct pre-peak in the structure factor. And the difference between strong nickel and less strong nickel is shown across the bottom here. There's a distinct peak below 2 inverse angstroms, and that corresponds to strong nickel-nickel ordering at a length scale of about 5 angstroms. 5 angstroms is way too far for a distance between metal atoms, so there has to be at least one more atom in between. So what we have here is strong aluminum ordering surrounding nickel and a tendency to have nickel, aluminum, nickel coordination inside the glass that is, again, stronger than you would expect from just randomness and the composition. So the dense random packing model fails to account for this kind of chemical short-range order, and that led to models that incorporate efficient packing and chemical short-range order. There are two sort of significant ones. One of them is, again, from Dan Miracle, and he emphasizes solute-centered clusters. So clusters that are centered around the minority composition element in the alloy, but subject to the efficient cluster packing rules associated with the difference in atomic size between the solute and solvent atoms shown here in blue and in pink. And then, in order to allow for alloys that have more than 2 elements, if you've got a third or a fourth element in the composition, it gets shoved into the interstitial spaces. So the insight here is that we'll have solute-centered clusters. These sort of act like big atoms. They then pack together at a next longer length scale, and the additional atoms fill in the spaces that are in between the packing of our larger clusters of atoms. In this paper, Miracle talks about FCC and BCC packing of these solute-centered clusters. You should not take that seriously because if there was such strong order of the solute center atoms, it would show up as Bragg peaks in diffraction, which are definitely not there. It's just a way to build out the next longer length scale of order beyond these nearest neighbor clusters. And then a few years later, Howard Sheng and Evan Ma did an extensive analysis based on XF, scattering data, and simulations to identify a few dominant, what they termed quasi-equivalent solute-centered clusters for a variety of different types of glasses. So here's an example of zirconium platinum, and here are the statistics of different Voronoi indices for an atomic model of zirconium platinum. There's quite a lot of 0, 0, 12, 0 clusters. Those are perfect icosahedra. The next highest one, or the next, another prominent cluster is 0281, which they argue is an icosahedron in which one of the atoms has been moved a little bit too far away to have the perfect geometry, but therefore is quasi-icosahedral and ought to be lumped together with the icosahedron. So this is a way to account for a level of disorder in the atomic models. They then pack together these quasi-equivalent solute-centered clusters every which way. So if you have a polyhedron, they can pack together by sharing faces, edges, or corners. And in the Sheng and Ma model, that's what happens with no particular preference for any kind of polyhedral sharing to pack together the solute-centered quasi-equivalent clusters to make out the full solid. Now, of course, not all glasses have this icosahedral short-range order. In particular, glasses that are a mixture of metals and what metallurgists call metalloid atoms, particularly boron, carbon, silicon, and phosphorus, have a different icosahedral short-range order motifs. And that is associated with the fact that there is some directional bonding that comes in from the metalloid atoms, and because of the large size difference between the metals and the metalloids leading to low coordination numbers. So there's a whole zoo of different polyhedra for different kinds of species. I won't go through all of them except to show you a few examples. Here's a standard trigonal prism with 3 atoms. Here's a bicapped square antiprism. Here's a Z9 Frank-Casper polyhedron. You can find predictions in the literature for different compositions as to what the dominant short-range motif is likely to be given the species and the coordination number. But then they fit together in the same kinds of ways that we've seen previously. So this is a pretty good description of the short range order, nearest neighbor and next nearest neighbor for metallic glasses. We can get a little bit of additional information by doing diffraction at very short length scales using focused probes of electrons. So it's possible to make electron beams that are a nanometer or less in diameter and measure Bragg diffraction using them. There are 2 techniques based on this fundamental technology. One of them is called Angstrom beam diffraction, despite the fact that the beam is about half a nanometer. So it's a couple of angstroms rather than 1, but it sounds good. And these are Angstrom beam diffraction patterns from a zirconium platinum metallic glass. On the left-hand side here are experiments, which show some sort of blurry features, but those features arise still from diffraction from essentially one nearest neighbor cluster of atoms at a time. And on the right-hand side are simulated diffraction patterns from the clusters on the shown on the far right in a particular orientation selected to match the experiments. So what this allows the experimenters to do is to say, we have uncovered evidence that these clusters exist somewhere in our glass by this kind of matching process, one-to-one. My group has worked for many years on a technique where we acquire a large number of diffraction patterns, and rather than trying to analyze each one individually, we look at the statistics of lots and lots of them, and in particular we look for fluctuations in intensity from place to place, which is what gives the technique its name, fluctuation electron microscopy. And from those data, we have discovered that at least two types of metallic glasses exhibit a competition between two structure types, one of which has local six-fold rotational symmetry, which we call crystal-like because that's a crystallographically allowed rotational symmetry. Here's a chunk of a model of a zirconium copper aluminum metallic glass showing oriented down the six-fold axis, one of the six-fold axes for this ordered region. Here are computed views of the reciprocal space for the model showing the six-fold ring. And that crystal-like structure competes with icosahedral-like structures, which in our models tend to form chains. And we think the reason they do that is viewed down the chain axis, the atoms tend to form planes, which is what's doing the diffracting. And these chains of icosahedra are similar to structures that arise in quasicrystals that also give rise to strong diffraction. So the reason that all of this kind of structure is important for metallic glasses is that it contributes to the processes and properties of the materials. So just to give you two examples of how that works, the structure of metallic glasses and liquids contributes to the glass-forming ability of a particular composition. That's its ability to quench into a glassy state, avoiding crystallization. That's been shown in simulations here, where the red line is the fraction of icosahedra in a melt, which increases dramatically right at the glass transition from the high temperature into the glassy state. And these icosahedra also have slow dynamics. They move slowly. And in our work, we've shown that good glass formers become more icosahedral as they're annealed and relax down to lower enthalpy states, whereas poor glass formers become more crystal-like. Okay, and finally, the local icosahedral order also influences the plasticity of metallic glasses. Plastic deformation in metals is inhomogeneous. It tends to localize into shear bands. That makes metallic glasses globally brittle. All the deformation gets packed into a 10 nanometer wide band that then fails at very low global strain. And simulation shows that the regions where deformation starts, shown in red on this map here, avoid tightly packed five-fold symmetric regions shown in black. And then the deformation propagates in between these black regions until it finally penetrates them at significantly higher strains. Okay. I'll also touch on, although not cover in detail, two more classes of materials, one of which is molecular glasses, which are essentially a dense random packing of non-spherical objects, as long as the molecules have predominantly van der Waals bonding in between them. So here are some examples of rod-shaped molecules of different lengths and disc-shaped molecules with different molecular structure. Please no one ask me what the molecules are. I know about this much organic chemistry. If instead there are hydrogen bonds between the molecules, you end up with a more directional bonding network, of which liquid water and water ice is the sort of prototypical example. One of the intriguing structural effects of random packing of non-spherical objects is it's possible to create materials that have a preferred global molecular orientation, so they are globally anisotropic, but still don't have any long-range order. And examples of a sort of rod-shaped molecule are shown here, where this is X-ray scattering data showing that the molecules mostly lie down in this class and mostly stand up in that one with respect to a substrate for the thin film growth. And here is optical birefringence data showing similar things for a different molecule and its influence on the optical properties of the resulting thin film. If we keep going with the idea of directional bonding, we arrive at covalent network glasses. Examples include silicas, chalcogenides, and amorphous group 4 semiconductors. So these have very strong directional bonding, and therefore both preferred bond lengths and preferred bond angles. So the building blocks are sort of little tetrahedra that then connect with one another. Then the variability can come by twisting one polyhedra with respect to the other one around their common bond. That's called the dihedral angle, because it's one tetrahedron and another, so dihedral. That introduces randomness, so the structure can be characterized by a distribution of dihedral angles, but also by counting rings of bonds or other topological bonding measures that make little clusters. And an example of how this sort of network of bonds can connect to properties is if you think about the mechanical properties of a network, they vary with the number of interconnection between the nodes of the network. So here is a two-connected network that looks mostly sort of like a long polymer chain. And you can imagine that it would be easy to shear this object without changing the bond angles or bond lengths very much. Whereas on the right-hand side, we have a more connected tree network with multiple connections for each one of the nodes. This object will be more resistant to shear without changing the bond angles and bond lengths. Okay, so I'm going to hand this back to Paul, and he will tell us more about the structure of more complex oxides with more complicated building blocks.
So in the last couple of minutes, I'm going to build on what Paul talked about and start to generalize towards the types of oxides that you might see. You might see that more multi-ion, multi-metal ion compositions would make. So if we go back here to this idea of building blocks, you've seen the molecular building blocks and the simple bond-ordered building blocks that characterize the glasses that in the last few classes. But now we can start to think about building materials where you require the ions to be coordinated with oxygen. And ions will form lots of different types of building blocks. In SiO2, you'll find that there are tetrahedra, and that the correct way to build up this is SiO2-like quartz, the correct way to build a molecular glass out of this, or to build a glass out of this, I should say, is to have these tetrahedra share corners, and just build a solid where you follow that rule. If you want, if you want to modify the properties of the glass, you have to disrupt that network, change it. And that's done in glass technology all the time. And in fact, every glass around us has a series of dopants that modify this network. So window glass, the glass that we make containers out of, fiber optics, everything has properties that are defined by dopants that define this, that change this network. There's a vast technology of this that is a subject of entire careers and industries. So there's a beautiful book and many other references. But the key to keep in mind is that this is the building block that's being disrupted. It's not necessarily that they have to share corners or they have to be even tetrahedra. So if you look more carefully, if you start to go back to this question of what would the crystals look like, you can start to think about how the oxides make crystals. And the oxides will make crystals by building tetrahedra and octahedra mostly. And you can start to think about how they're arranged in crystals or how you would arrange them in a glass where you require the local coordination to be correct, but the global coordination, the global order is not there. So the crystals have repeats of octahedra and tetrahedra. The amorphous materials in the glasses have these octahedra and tetrahedra, but somehow pack them in a way that lacks the long-range order. Okay, so that actually works. This is a phosphate glass molecular dynamics simulation. You can see there are the tetrahedra here, and I won't go into the structure very much except to say that the molecular dynamics type of prediction that you would make of this glass fits with the X-ray and neutron scattering data. So you can accurately work back and forth between this structural type of idea of forming bigger building block materials, amorphous materials, and the scattering data. In other glasses, like Al2O3, you don't have to have just corner sharing tetrahedra. You can have edge sharing tetrahedra. Can you see this here? There's oxygen is the fat one, and the little one is the aluminum. Here, the aluminum O tetrahedra share a corner. Here, the aluminum O tetrahedra share an edge, and many of the properties of Al2O3 are defined by this type of geometric consideration. But we can generalize this even more, and we can start to say, well, what happens if I don't know this and I want to learn about it? So that's the last thing I'd like to do in the last couple of minutes, is to show you a couple of examples where we don't a priori know much about these amorphous materials. We'd like to use some geometric descriptions to understand their properties. So here now we've crossed from well-defined things, well-accepted glass models to some uncertainty in the literature. So let me point this out. This is a material strontium titanate. It's a perovskite. It forms in the in the crystal it'll form a simple cubic structure with an octahedral arrangement around the titanium. In the glass, you can do an X-ray spectroscopy experiment that seems to show that there's tetrahedral TiO coordination, which may inhibit crystallization. But the literature is actually, even though this was only 10 years ago, and this is the model perovskite, is actually somewhat ambiguous on this topic. So here's a relatively simple material where we don't know much about the amorphous structure yet. It's kind of interesting, and it will define some of the types of stability arguments that Paul has just talked about. Let me show you another one and show you how partial information can be useful in designing these materials, and show you sort of the state of the art in thinking about how to work with the structures of complex oxide amorphous materials. So this is an example that's drawn from some work at Northwestern. In fact, was in their MRSEC's studies of amorphous oxide semiconductors. In contrast with much of what our MRSEC is trying to do, they do not want to crystallize these semiconductors because the semiconductors that they want require the amorphous structure to be uniform throughout and to avoid nanocrystals. So what they would like to have is indium oxide. They dope the indium oxide with gallium so that the resulting amorphous structure is maintained at high temperatures. And so here's a study of the crystallization temperature as a function of the gallium content. And what you can see is that the crystallization temperature climbs as the gallium content climbs. The question is, why is it harder to crystallize an amorphous solid that has this seemingly similar chemically similar gallium in replacing the indium. And if you look at what eventually forms by the crystallization, it's gallium-doped indium oxide. It makes a lot of sense. But the question is what's going on in the amorphous structure, and can we get some insight without learning all of the structural details? So if you look carefully, you have structures locally that look around indium look like indium oxide, that around gallium look like gallium oxide, Ga2O3, but something's wrong. And so if you go and you do the pair distribution function analysis more carefully, you'll find that the gallium coordination is not quite right. So let me show you this. This is the partial pair distribution function data, and this is the crystal gallium oxide is in black. Okay, see the black? The red is the total PDF. Okay, we can ignore that. That's just all the atoms. The green is this differential PDF, and you can see that the gallium is like it's in gallium oxide, but not quite. And what's going to happen there is that if you go look carefully at what would be required to match this PDF, you'll find that the gallium is not in a position to crystallize, and that the gallium inhibits the formation of the Ga2O3 and inhibits the crystallization of the whole material. So if you go back and you match this pair distribution function with a molecular dynamics simulation, here's what the simulation shows you. It's a little bit hard to see, but what I want to show you is that this is the gallium-oxygen coordination that matches the PDF. If you look carefully, these green here is the highest gallium concentration. You can see that the gallium concentration drives the gallium-oxygen coordination to higher numbers. It drives it away from the bulk where the bulk structure would be. And the argument is that by driving this system to a configuration of the gallium that's different than the bulk, that you inhibit the crystallization. Okay, that's the fundamental argument. Now, you can argue about whether that, we'll have to argue about whether that is sufficient to design materials or not, but it certainly describes the structure and its stability. Let me show you some other examples. So in this case, the structural information informs what's happening, at least. Here are some other examples where it's less well known what's happening, and sort of represents, in my mind, the state of the art in trying to predict maybe what we could do if we could understand and control these structures better. So this is an example drawn from vanadium oxide. Vanadium oxide is a fascinating material because it can have multiple crystalline forms. It has multiple polymorphs, and you can select the polymorph, apparently. This was discovered in 2016 by a group from NREL and collaborating with a characterization team at Stanford, where you can select the amorphous structure by changing the deposition rate and deposition conditions of the amorphous material. So these are the green and the black are slightly different X-ray scattering distributions. The bottom is the G of R extracted from those. And the key thing is that if you start with the green and start with the black, you end up with different crystalline polymorphs. Fascinating. Totally, I would say, totally unknown what local structure is driving the selection of the polymorph from these materials. Okay, so that's in VO2. It's highly interesting. And let me go back and show you one thing from MRSEC's work. This is Yajin Chen's work on strontium titanate. And what I want you to do, I'm showing a very narrow range of X-ray scattering Qs here. In fact, it's not even plotted as Qs. It's plotted as 2 thetas. But if you look carefully, right before it crystallizes, it actually changes the shape of this amorphous peak and shifts it a little bit to the right. So the question is part of the crystallization process a reconfiguration of the amorphous form of the material? And as you can see, there's an incredible range of powerful tools available, and there's these open research questions in terms of the impact of the amorphous structure. So that brings us to the end of the oxides, and I just want to draw some sort of general statements out of that, and then wrap up with the conclusion. So the key thing from the amorphous complex oxides that we've seen is that we have these amorphous X-ray scattering patterns, and there's no simple rule. You can't work, you can get the G of R's, of course, and the partial pair distribution functions, but often there's no simple rule for interpreting them the same way that you would interpret an X-ray crystallography study. And so what you end up in many times doing is combining them with a molecular dynamics calculation that allows you to test a series of structural models. And you can see that also in the work that Paul presented. So for example, the molecular dynamics would tell you what candidate structures you might be seeing, and that you can in general unravel the key local configurational issues by combining it with some spectroscopic information from X-ray absorption spectroscopy or from these partial pair distribution function or radial distribution function methods. So that's the state of the art, and you can see that in comparison with the understanding of the metal, the metallic glasses, the amorphous complex oxides are still at a relatively early stage. Okay, so finally, let me wrap up for everything. This is the summary for both parts of the presentation. The key things to take away from today are that these amorphous solids are easily defined, that they lack this long-range translational order, they have strong short-range order, that the short-range order is intuitively understandable, I should say, by characterizing the interatomic bonding, that you can think about geometric models. They can become somewhat sophisticated and geometrically complicated, but that you can think about them as being driven by effects that are local and that you can understand. That there's packing efficiencies, there are directional bonding networks, the formation of polyhedra in the metal oxides that you can pack, and you can come up with rules that would allow you to define the short-range order and to build things that you can compare. And a good place to start is thinking about building from the local structure of crystals, but allowing a degree of disorder in the local structure. And finally, there are lots of ways to characterize the amorphous structure. There's no definitive way to do it yet, or perhaps ever, but there are many, many ways to compare, and that simulations are a key part of doing that. And finally, the key thing to take away is that if we can understand this structure, that it impacts all the properties of the resulting material. And there are key structural considerations, in fact, structural knobs that we can use in designing materials that will define the crystallization, the stability, the mechanical and electrical and electronic and other properties of the materials. So with that, we're at the end of the lecture. I think both Paul and I are available to take questions if you like. Thank you.
We should also say we're a few minutes over.
Yes, we apologize.
Anyone who needs to make their way out the door, please feel free.
So,
Leave that charge.
yeah, how appropriate and model is for the classes? Like we have seen evidence on both sides in the slides.
So the question is, how good is the random packing model? So I think for nearest neighbor order in metal glasses, so all stay away from the right-hand side of the periodic table. The efficient cluster packing models work really pretty well. So dense random packing, meaning literally completely random, knows nothing about chemistry at all, is demonstrably wrong, but the efficient cluster packing models are pretty good. Then the question is, are the properties that you're interested in determined to your satisfaction by knowing only the nearest neighbor structure? If the answer is yes, then you're done. And if the answer is no, then you'll need something on top of that efficient cluster packing. And crystallization, for example, involves formation of crystal nuclei that are larger than nearest neighbors. So efficient cluster packing will get you some distance, but not all the way to understanding of the process that you'd like to understand. Anything else?
Can I ask a question?
Yeah.
Okay, Paul, Paul Young. So for silicon, actually, my student worked on the amorphous semiconductors. In general, you show all the examples, like first PDF or first sheet. Ask how they work and how they work, right? Most examples. So the amorphous silicon is an actually the first the silicon bound field, okay, is the sharper than any other crystal tetrahedron. So look like in amorphous of the last silicon SiO2, more like ideal and particular and stay same size, exact same size. So that's a little bit surprising to us.
Well, I think that, I mean, that I think of course that first peak has launched 1,000 ships. So there's a lot of interesting discussion of the meaning of that first strong maximum in especially in the SiO2 literature. You can, but one thing to keep in mind is that the crystal often has to compromise some sort of packing issues to be able to form the long range order. So you could have crystals where some atoms are less happy, it's from a thermodynamic perspective, than they would be in a glass. And so the bond ordering could actually be improved. So you can think of crystals where there's a bond that's a little bit too long. And the oxides are famous for this because there's a concept, there's all these concepts about rotating octahedra and distorting bond lengths and having trade-offs that trade off all of those quantities. So I'm not aware of that particular example, but it's not so surprising to me that you might find situations where, for example, all the silicon atoms get to sit in the right place, whereas in a crystal, maybe half get to sit slightly frustrated. And that would often define the stability of polymorphs, for example, in the bulk. And so maybe something like that is happening in the vanadium oxide case also. An excellent question.
A question for the Angstrom diffraction sort of technique that you're talking about, Paul. And you were talking how they found this match between some like idealized structures. How sort of likely is that? Or like how much is it where if I was going, I could just be like, oh, I'm just going to take this around and look, that's a great match.
Yeah, so you're asking sort of what is the statistical rigor of the Angstrom beam electron diffraction experiments?
Sure, yeah.
This is a thing about those papers that makes me itch. Their procedure is to generate ab initio molecular dynamics models, pluck clusters out of those models, and then try to simulate diffraction from all those clusters and match them to the experiments. If memory serves, they claim to find matches somehow for about half of the experimental patterns to clusters that they find in the simulations. So I think that with a little careful wordsmithing, you can make the conclusions rigorous. So I think it is correct to say that the clusters that they have identified as matching the patterns do exist in the glass. That is not the same as saying that they are dominant or important or statistically significant. It's a sort of existence proof only. But I think as an existence proof, it's correct. Sean?
Whenever the version, okay, that beams force are smaller than inner cell. Okay, for error is no problem. Inner cell is small. For my crystal, always large inner cell.
Sure.
So, because I still don't understand the reason to use beam smaller than inner cell, then of course there are something. The interpretation is like it's very difficult for my crystal.
Yeah, so those Angstrom beam diffraction experiments, they're done on metals, so they're really trying to match the probe size to the size of a nearest neighbor cluster. So they're using like a 4 angstrom probe, that's sort of two angstrom bonds across. Now if you can make an angstrom size probe And if you use one of those to do diffraction from a glass, what you find out is that the glass is made of atoms. And you kind of knew that already, so there's not a lot of useful additional information at super high spatial resolution in electron scattering or electron microscopy from glasses.
How does the thickness of the sample affect the Angstrom?
So this is the other thing that makes me itch a little bit about those experiments. Their samples are 1 nanometer thick.
Oh.
And then that makes you wonder, to what extent is a 1 nanometer freestanding membrane of metallic glass that has been exposed to air characteristic of the structure of the bulk glass? And that's just really hard to say. Well, we can talk about that more afterwards.
There's a secret the source.
So maybe I can add something to the question about matching the probe size. If you look at this diffraction pattern here, the key is that you've lost a lot of information. That the averaging that is inherent in doing this incoherent average over many instantiations of the glass has destroyed information. So any way that you can avoid the average would be mathematically equivalent. So you can either look at a small sample volume, or you can create a probe that has phase coherence across the whole thing. But you need to do something that avoids looking at the average, because the average has destroyed all of the orientational information, and in fact smeared out the bond length direction information as well.
Any other questions? In that case, thank you all for coming.
Thanks, everybody.
Conclude the lecture.